Hi, Monica, and today I'll be presenting Group 2 Statistics Project on Chapter 2 Probability. Alright, so let's get started with a little bit of history. The Nuova Chronica, which is the first ever recorded probability book, was found in the 14th century by a History of Florence by the Florentine banker and official Giovanni Villani, which includes much statistical information on population, ordinances, commerce, trade, education, and religious facilities, and has been described as the first introduction of statistics as a positive element in history, though it is important to know that neither the term nor the concept of statistics as a specific field yet existed. Mathematical methods of statistics emerged from the probability theory, which can be dated to the correspondence of Pierre de Fermat and Blaise Pascal in 1654. Christian Huygens in 1657 gave the earliest known scientific treatment of the subject. Jacob Bernoulli's Ars Conjectandi, the posthumous of 1713, and Abraham de Moivre's Doctrine of Chances in 1718 treated the subject as a branch of mathematics. In the modern era, the work of Kolmogorov has been instrumental in formulating the fundamental model of probability theory, which is used throughout statistics. Although statistics requires basic math skills, it is not categorized as mathematics. Alright, so now let's start with a little bit of definition so that we can be on the same page. An experiment is an act or process of observation that leads to a single outcome that cannot be predicted with certainty. There are two probability rules, and those are that all sample probability must lie between 0 and 1. It is important to know that probability is often expressed in a decimal or a percentage, which leads to the second rule, in which the sum of the probabilities must be 1. An event is a specific collection of a sample point, and a sample point or sample space is the most basic outcome of an experiment, and sample space is the collection of all of its sample points. All possible outcomes are called sample space. For example, when flipping a coin, we have two sample points. Can either be heads or tails. But when tossing two coins, we can either get a head first and another head, or we can also get a head and then a tail. If we keep going down the sample space, we will find that we can also get tails, heads, or tail, tail. Here's a table showing the probability of tossing a coin, where one could get 3 heads, no tails, shown on the right, and when we can get 2 heads, 1 tail, 2 heads, 1 tail. We can also get 1 head, 2 tails, picking on the right, or all tails. These tables are often very useful because they give an illustration of really what the probabilities would look like. Sample spaces and probability. We are asked to write the sample space for the given experiment, in which a dollar coin and a 50-cent coin are tossed. When 2 coins are tossed, we can either get heads or tails, tails or heads, 2 tails, or 2 heads. This would be our answer, the sample space. All the possible outcomes in order. It is important to remember that although we can have heads and tails, tails or heads, the order of the outcome does matter. In our second example, a card is selected from a deck, and we're asked to find the probability of finding an ace. Out of a deck of 52 cards, 4 of them are an ace. Simplified, we have 1 over 13, which gives us a probability of 7.69%. In example number 3, we have a bag containing 5 pennies, 4 nickels, and 6 quarters. If a coin is chosen at random, what would be the probability of choosing a penny? Total, 5 plus 4 plus 6. Total of 15 coins in the bag. Now we're asked about the probability of pennies. Since there are only 5 pennies in the bag, we'll put 5 out of 15. Simplified form would be 1 out of 3, 1/3, which is 33%. On our next example, we're asked to consider a family of 4 baby crocodiles. We have to find the probability of 3 males and 1 female. First of all, we start by writing the sample space. This problem, the order of the outcome does not really matter, since what we're really looking for is that no matter the order, we will find 3 males and 1 female. We find that out of 5 possible outcomes, only 1 of them matches the description of 3 male, 1 female. Therefore, the probability of having 3 males and 1 female is 20%. On our next example, 2 dice are rolled, and we're asked to consider the probability that the sum of the dice will be 4. Then again, we start by writing all of the possible outcomes of rolling 2 dice. 36 outcomes total. And then we look for the one that matches our description, which would be the sum of the dice is 4. We find that only 3 out of the 36 possible outcomes match the description. 3 over 36, which is further simplified into 1 over 12, which is 8.33%. Mutually exclusive events and the addition rule. Mutually exclusive events are 2 events that are mutually exclusive or disjoint. This is a key word. If it is possible for them to occur together. Formally, 2 events, A and B, are mutually exclusive if and only if A is disjoint from B, and that is equal to 0. On our first example, determine whether the following pair of events is mutually exclusive. A card is drawn from a deck. The probability of F, if it is a queen, probability of G, it's a diamond. Are these mutually exclusive? The answer is no. The event is not mutually exclusive because one can draw a card of Queen of Diamonds, which means that both events can occur at the same time. On our next example, we have the addition rule. A fair dice is rolled, and the events H and I are as follows. H, the probability that an odd number will show. I, probability that an even number will show. The probability of, first of all, we start by writing the sample space, the probability of H. Odd numbers in the dice, 1, 3, and 5. 3 out of 6 gives us a 50% chance. The probability of drawing an even number, 2, 4, and 6. Then again, 3 over 6 gives us a 50%. This event is mutually exclusive because both events cannot occur at the same time. See, compared to the other example that we had, we can have a queen and a diamond. But in our next example, we cannot have a number that is odd and even at the same time. That's the difference between our mutually exclusive. On our next example, we have a table showing individuals classified by either being Persian, American, male, or female. A total of 100 individuals. Example number 1 asks us for the probability of a male given that they're Persian out of a total of 100 men. We have 39 male Persians for a total of 39%. Probability of the individual being a female given that she's American. American, female. I'll have 5 over 100. Example number 3 asks for the probability of a male given that he is Persian. Have a 95 over 100, giving us a total of 95%. The probability of a male or a female is 0.5. Moving on to independent. One must understand that an event can either be mutually independent or independent. It cannot be both at the same time. The distribution of the number of folklore and children's books checked out of a city's main library and at a smaller branch on a given day is as follows. Here we have a chart showing the main library and the branch. Folklore books, children books, out of a total of 550 books. The probability of getting a children's book